Let's take a look at this question. An object moves along a path given by this equation. Find the value of dy dt at an instant when some other things are true. Okay, so before we get into the details of this question, let me try to give you an idea what's going on. An object's moving along a path. So for example, this path might represent the trajectory of, say, a ball that's been thrown. Picture someone throws a ball and it arcs through the air like this. This sort of path of the object, that's what's being described by this equation. So as the object moves along this path from left to right, it's going up and down, so the y-coordinate is changing, and it's moving from left to right, so the x-coordinate is changing. So you can think of the coordinates of this object, the x and y coordinates, both as functions of time. Your x is really some function of t, your y is really some function of t, where t measures the moment in time. So maybe the object starts out right here when t is 0. And at some time later on, maybe when t is 1, the object ends up somewhere else. Now the fact that the path has this equation tells us that the position x and the position y are related to each other. Those two functions of time are related to each other by this equation. And therefore, the rates at which those x and y values are changing are also related to each other. Here's how we can see that. Another way to write this equation would be as follows. The y on the left side, you can think of that as y of t, since the y position of the moving object depends on time t. And this expression on the right side, wherever you see an x, you can really think of that x as a function x of t, something that's changing as time changes. Now, in the kind of problem we're introducing here, a related rates question, we usually don't write this out. You usually do not make it explicit that y is a function of t and x is a function of t and write y of t and x of t. We normally don't do that. I'm doing it now just to illustrate what's going on here. Because the next step to find a relationship between how fast x and y are changing is to take a derivative of both sides of this equation. So if the function on the left side and the function on the right side are equal, that means they're the same function. And therefore, the derivatives of the two functions should be equal. Okay, so the derivative of y of t, we could write that as y prime of t. And on the right side, I have negative 16 times this quantity x of t quantity squared. So that's a composition of functions. You have an inside function x of t inside another function that squares it, so x squared. So I want to take the derivative of that expression. If I do that, I have to take the derivative of the outside function, x squared. That gives me 2x. Plug in the inside function, which is x of t, and multiply by the derivative of x of t, which we would write as x prime of t. So that's just the chain rule there. On the next piece, it's not as complicated. I just have 40 times x of t, and so the derivative will be 40 times x prime of t. And then the derivative of the constant 6 will be 0. Now let's write this another way where we don't have as much clutter. Instead of y prime of t, I'm going to express that derivative with the notation dy dt. And on the right side, I'm going to stop writing x of t. I'm just going to write x instead. So for example, this expression at the beginning becomes 16 times 2 is 32. Negative 32 x instead of x of t. And instead of x prime of t, we'll write dx dt, which means the same thing, plus 40, again, dx dt. What we have in this line is now an equation that relates dx dt and dy dt. dx dt is how fast the x position of the object is changing. dy dt is how fast the y position, or the vertical position of the object is changing. So if we plug in the value for dx dt is 20, and if we plug in the value for x is 3, we can find the value of dy dt when those two things are true. So when dx dt is 20 and x is 3, we plug that into this equation and we get dy dt is negative 32 times 3 times 20. So that 3 is replacing x and the 20 is replacing dx dt, plus 40 times dx dt. Again, dx dt is 20. So this comes out to negative 1,120. All right, that's how fast the y-coordinate of the object is changing. Since the y-coordinate is the vertical position of the object, we could interpret this as saying that the object is moving downward. The y-coordinate's decreasing at this rate. And if we had units on this question, maybe this is something like moving downward at 1,120 feet per second. By the way, these numbers are not realistic.